Welcome to Intro to Related Rates. So the idea here is we have lots of functions that relate real world variables, right? Or we have lots of equations that relate real world variables. So we have lots of equations that relate real world variables. So it would seem reasonable that we should also be able to use these equations and differentiation to relate rates. So we should be able to use these equations and differentiation to relate rates. So, for example, we know that the circumference of a circle. So we know that the circumference of a circle is given by c equals 2 pi r, where r is the radius. So we might ask, as r changes, how does c change, right? So as the radius changes, how does circumference change? And so we could just take the derivative of both of these with respect to time and see what happens. Right? So I'm going to give myself a little more space. So if we differentiate with respect to time, we'd be looking at the derivative with respect to time of c is equal to the derivative with respect to time of 2 pi r. And this would give us the derivative, the rate the circumference is changing as time passes is equal to 2 pi times whatever rate the radius is changing at. So if the radius is increasing at 1 centimeter per second, then, or 1 centimeter per minute, then the circumference will increase just 2 pi times as fast, right? So what we get is the circumference increases or decreases 2 pi times as fast. So for another example, we know the area of a square is given by A equals S squared, right? Again, where S is the side length. And so if we differentiate both sides, then we have both sides with respect to time. So imagine that area and side length are both functions in terms of time. We can differentiate with respect to time. And the chain rule, essentially we're doing implicit differentiation. We have the derivative with respect to time of A is equal to the derivative with respect to time of S squared. Again, we're just doing implicit differentiation. We wind up with the ADT on the left. And on the right, we would do the derivative of S squared with respect to S. So we're going to differentiate, oops. We're going to differentiate S squared with respect to X and then multiply by ds dt, right? That's how our implicit differentiation worked. And so we wind up with the ADT is equal to 2s times ds dt. So what we have here is how fast the area is changing is going to depend not only on how fast the side length is changing, but how large the side is to begin with. So note how fast the area is changing. Depends on both how fast the side length is changing and the current side length. So we're able to relate the rates here, but it's a little more interesting than just the radius and circumference, where it didn't matter how big the circle was, however fast the radius was changing, the circumference was just 2 pi times that. Here for the square, when we talk about area, however fast the side length of the square is changing, there's more information needed to know how fast the area is changing. So the larger the square is to start with, the faster the area changes, even if the side length is increasing at a steady rate. So let's go ahead and look at one more example, and then we will actually solve related rate problems and see what we are doing with this information. So for another example, let's consider let's do the volume of a cone. So the volume of a cone is given by V equals 1/3 pi r squared h, where r is the radius of the base, and h is the height of the cone. So what we get if we differentiate both sides with respect to time we're looking at d dt of v is equal to d dt of 1/3 pi r squared h. So on the left, we just have dv dt. And on the right, we will have 1/3 pi, and then we'll have to do the derivative of r squared h. Now this, we have a product rule. As unless they tell us that height it doesn't change or that radius doesn't change, then we're stuck with viewing both r and h as two separate variables, two separate functions of t. So we will do the product rule. This is 1/3 pi times, we'll do the derivative of r squared with respect to t times h plus r squared times the derivative of h with respect to t. And so we wind up getting dv dt is equal to 1/3 pi times, we would have 2r dr dt times h plus r squared times dh dt. Right, so again, we have to do implicit differentiation. So that r squared, we differentiated with respect to r first. Power rule says it's 2r. And chain rule said we multiplied by dr dt. So again, this was from here to here, we used the product rule. And then from here to here, we're using implicit differentiation or the chain rule. So this is sort of a intro to how we can go about finding these equations that relate rates. And it starts off with just the equation that relates the initial variables, and then taking the derivative implicitly with respect to time allows us to relate rates.